Hi Heather, so here's a video to walk you through the mean value theorem problems. I made one yesterday, but apparently it accidentally got deleted, so here we go. Okay, so the first part is about Rolle's theorem. And we see Rolle's theorem here, and it says, now for both the Rolle's theorem and the mean value theorem, we're going to assume that our function, whatever we're talking about, f of x, is continuous on some interval. So we're always kind of just looking at a little piece of the function, and we call that interval from a to b. And it has to be differentiable at least, most of the time we're just going to be talking about polynomials, things that are always differentiable. But it at least has to be differentiable on the open interval, meaning we don't really care about the endpoints. Most of the time that's not going to matter. Now, for Rolle's theorem, we put this extra condition that the endpoints of the interval, the function has to be equal, meaning f of a has to equal f of b. So this is just the same as saying the y values of the graph at a and b are the same. Okay, then what Rolle's theorem says is if this is true, then there is some c, so some other x value c between a and b. So there's some x value on that interval where the derivative of the function at c equals 0. So we're just saying there's some point where the derivative is 0. So from what we've done, after this, that means there's some point where there's a max or a min. Okay, the next part on the notes right here, this y, that's just to kind of draw a little picture to help, convince yourself of it. So all this is saying, let's say we've got our xy plane and we're just picking some interval from a to b. Okay, and this condition right here, that f of a has to be equal to f of b, means whatever the y values are at a and b, they're the same. Okay, now think about it. If let's say from a we started to go up. At some point to get back to f of b, we'd have to start coming down, right? And since it's continuous, we can't have any gaps or jumps or asymptotes. So there has to be some point where there's a maximum, and at that point, that's the c value. Okay, and so same thing, just kind of a different possibility. If we started going down, there'd be some place where we'd have to go back up. So there'd be a place where we have a minimum. Okay, and even if we went up and then down, you could have more than one place where the derivative is 0. It's just saying if those values are equal, we have to have at least one place. And the one other thing that kind of could happen is that it could be constant the whole time. Okay, meaning we could just have a straight line. Well, in that case, the derivative along there is always 0. Okay, so that's just the first part of the notes explaining what Rolle's theorem is. Now, the mean value theorem, okay, we don't care about f of a equaling f of b, and it's actually more general. And what it says is that, if you're differentiable, there is some point c. So this is the mean value theorem, which we just say MVT. So for the mean value theorem, okay, there is some point c where, so remember we have our interval a to b. And so we're saying there's some point c where f of b minus f of a over b minus a is equal to f prime of c. Now, this should look like a slope to you, the left-hand side. What this really is your average slope. And this is your instantaneous slope. Remember the slope of the tangent line at c. So what we're saying is if you've got any function, okay, and you pick any two values, let's say this is a and this is b down here. Okay, so if we took this, the left-hand side, f of b minus f of a over b minus a, what that really is the slope of what we call the secant line, the slope of the line containing there. So the slope of this line, m equals f of b minus f of a over b minus a, because what f of b really is the y-coordinate here. This was the point b, comma, f of b, and this point up here is a, comma, f of a. Okay, so the slope would be f of b minus f of a over b minus a. We're saying there's some point, and it can be anywhere between a and b, some point c, where if we took the slope of the tangent line, my drawing is horrible here, but the tangent line would be parallel to the secant line, and that means the slope, the instantaneous slope right there, is equal to the average slope. Okay, so the first example says find the value c that satisfies the conclusion of the mean value theorem for f of x equals x cubed minus x squared on the interval from -1 to 2. So x cubed minus x squared, so f of x cubed minus x squared on the interval from -1 to 2. Okay, so this means, so this says find the conclusion, find that c. So this is a and this is b. We want to find f prime of c to be equal to f of b minus f of a over b minus a. So if you plug 2 in here, we're going to have 8 minus 4, which is 4, minus, if we plug -1 in, we're going to get -1 minus 1, so we'll get -2, so minus a -2 over 2 minus -1 is 3. So we're going to have 6 over 3, or 2. So this is just saying find the value of c where the derivative at c is equal to 2. So if we take f prime of x, that's going to be 3x squared minus 2x. We want to find where is x. If we set 3x squared minus 2x, where is that equal to 2? Okay, so, I mean, one way to do it would be to move the 2 over. We'd have 3x squared minus 2x minus 2 equals 0, and then you could use the quadratic formula. Okay, so I'll let you do that. You know, this recording's only going to be 15 minutes, so I don't want to spend too much time there. Okay, now the next type of problem you see are these that say, show that this function has exactly 1 0. And here we're going to be using Rolle's theorem, okay? So we have x cubed plus 4 over x squared plus 7, and we want to show it has exactly 1 0 between -infinity and 0. So we want to show that f of x equals x cubed plus 4 over x squared plus 7 has exactly 1 0. Now here are going to be our steps. We're going to find a 0 to show that it has at least 1 0. Okay, then we're going to use Rolle's theorem to show there can't be 2 zeros. Okay, now one way to show that it does have a 0 is to use our graphing calculator. So if we put in x cubed plus 4 x to the -2 plus 7, okay, and we graph, we'll see that it does have this 1 0 between -infinity and 0. And normally you'd want to use the intersect feature and find that and find whatever that 0 is. Okay. Well, now we're going to use Rolle's theorem to show it can't have two zeros. So here's how we do that. I'm actually going to erase this just so I have more room. Okay, so we do something called contradiction, meaning we're going to assume, so this is actually going to be a proof, we're going to assume there are two zeros, which is the opposite of what we want to be true. We want to show there can't be two zeros. So if we find something that contradicts, is against Rolle's theorem, our assumption of two zeros will be wrong. Okay, so we're going to call our two zeros A and B. Well, what does it mean for it to be a zero? Well, for it to be a zero, it means f of A equals 0 and f of B equals 0. So I hope you see that that's the beginning of Rolle's theorem, because now we have f of A and f of B being the same thing. So what that means, what Rolle's theorem tells us, says there is some point C where f prime of C would have to be 0, right? But what happens if you take the derivative, so f prime, you know, this is the same as x cubed plus 4x to the negative 2 plus 7. If you take the derivative, f prime of x is equal to 3x squared minus 8x to the negative 3. And if you look at the graph here, there are no zeros of this function. Okay, so this contradicts. Since Rolle's theorem tells us there has to, but we see there isn't, that should say contradicts, not contracts. So this contradicts Rolle's theorem, so there can't be two zeros. Since we've shown it has one and there can't be two, that means there exactly. There's exactly 1 0. Okay, so that's how you do these problems. Now real quickly, just to go to this one about the toll booth, you know, actually I'll make a new video with number 4 and number 5.